We're good? Okay, perfect. All right. Thanks, everyone. So last month I talked about a foundational model, geospatial model from Microsoft, and so this month I'll be talking about one that is from IBM and NASA. So this one came before the previous one, but I'm just kind of building up my knowledge of all of these different models, and so this was one of the most significant ones. So this is a paper, NASA, IBM, a huge team worked on this. And so what they did is they wanted to pre-train a model that had a lot of knowledge from geospatial information. So they took their massive stores of satellite images um, and they used this to, um, we're using your, oh. Um, So they used these petabytes of satellite images, and then they said, let's train a model on all of these satellite images, and then use that and transfer it to other tasks down the way. So there's a big challenge here with just the size of the data that they have. So I'll talk more about the data on the next slide. And so the hope is that you train this model on these satellite images, and then it learns a bunch about the world. And then when you go try to do further classifications and segmentations and other things, you can take this model and transfer it to the new problem, and it will perform better and learn faster and all of these amazing properties. So the data set that they were working with is one from their own NASA store called HLS2. And this has it's a combination of multiple satellites, and then they've harmonized it. So the satellites are orbiting in different cycles, and then they line them all up, and they say, here's kind of the aggregation of all of the images from these different satellites. And so they have 30-meter resolution, and they also have a temporal resolution of every 2 to 3 days. So 30 meters is very, very high in the context of satellite imaging. So one pixel is 30 meters by 30 meters. If you look at other papers, like we looked at one before, 1 pixel was 3 kilometers. So this is like much, much finer grained. Um, and so the way that this is provided to people is they have these GeoTIFF files, and they're 3660 by 3660, and then it has 15 different spectral bands. So it might say like this specific image band is better for precipitation, and this one is better for looking at vegetation, and this one's good for ozone and stuff like that. So it's got 15 different bands, and they all have kind of their own specific purposes. And so all of this added together, and you go all the way back to 2015, it amounts to a huge amount of data. And so the first problem that they ran into this was you have all of this data. They looked even more specifically at the US, and then even then still, if you just randomly sample from the data, you're going to get lots of redundancy. So if you take one tile and then you go one tile over, it's probably going to look very, very similar because it's only a few kilometers away. Um, so what they did is they actually took this and they kind of aggregated it together, and they looked at precipitation and temperature, and they said, we want some variation out of this. So they clustered the regions into 20 different groups. And then we said, based on the amount of precipitation and the temperature, we're going to sample randomly from the 20 different groups so that we have better coverage. Because if not, you might just end up in the desert and you're just training on the desert more and more and more, and you're missing certain more interesting regions. So one of the first problems that they ran into was this data that I was talking about. It's got these GeoTIFF files that come in a big format, this almost 4K by 4K, and then you have 15 spectral bands, and then you also have, they were training on 3 time steps at a time. And so if you look at the amount of data that this is, every time they want to load something, they're taking this huge chunk, and it's got extra spectral bands that they don't even care about, and then they have to load 3 of them for all of the different time steps. And so if they wanted to load their unit for actually training, they load this huge file, and then they take a 224 by 224 crop, and then they throw away nine of the spectral bands, And if you like do the math on all of that, you realize you're doing 667 times more reading than you actually need to look at the training data that you want. And so this is just massively wasteful. And so what they needed to do was take this data, read it in, format it into a czar array, which is just this flexible format that they could kind of place this in, and then they can read from it more flexibly. Um, and so taking this from the GeoTIFF to the czar made it so that they could read it in much faster. And so this benchmark they show on the right side is showing basically the GeoTIFFs before were basically twice as slow, and now they can do less workers and keep their GPUs more busy. And so one of the other problems that is common with this satellite data is you have all of these satellites going every different direction and you don't have full coverage all the time. And so you might have actually missing bands within your data. And so they're loading this data in and they're realizing we loaded this chunk and actually there's a stripe across it that's just missing data. We just don't know what it is. And so they wanted to exclude those portions as well. And then there's also the problem with cloud cover. So if a cloud comes through, you're actually not seeing the surface, the part that you're interested in. You're just getting blocked by a cloud. And so they had to look through the images beforehand and basically say which of the regions are valid for us to train against, because we don't want to be training against blank data, and we also don't want to be training against just clouds when we thought we were looking at the surface of the Earth. And so what they did is they went through and they just kind of swept through all of the data and said, where are the valid places for us to actually train against and exclude that? Because if they did it randomly, if they just said, we're going to just sample from this data and just pick a random point, then very often they were wasting effort on that as well. So they pre-computed the regions and they reformatted it as czar, and then now they have a much more efficient pipeline that isn't wasting this huge effort. Um, so here's the architecture and the training process. So the architecture, I won't go into too much detail on because it's a VIT that they've expanded to handle 3D data. Their contribution though was not the architecture. Their contribution was putting the data through the architecture. So if you're familiar with VITs, they took the vision transformer and they just adapted it with 3D patch embeddings and 3D positional encodings instead of the normal 2D. So they just kind of expanded the dimension there. And the training process that they're doing in order to kind of distill this knowledge into the model is they're taking the images, they're breaking it into patches, and then they're masking out some of the image. So we've talked about this concept in some previous weeks. So this is a masked autoencoder. So what it's doing is it's masking out these blocks, and then the model just can't see that anymore. And so what it's doing is they're saying, okay, 50% of the image, blank it out in these squares, and then train the model to fill in the blanks. And so in doing that, it's understanding kind of the relationships and what the world looks like. And so with this, it can see we have this square here. What does the square next to it look like? It probably looks similar. It probably has similar features. And it can kind of infer based on the surrounding context what it should look like. So it receives this masked image and then it's trying to predict the original image again. And then we know the answer to that because we have this data from previously and we compare it and we train it. And then we run that process. They use 64 GPUs for many hours and all of these petabytes of data. And then in theory, we hope that what it learned from this is going to transfer to all of the different things that they want to transfer it to. So here's an example of what this masked autoencoding looks like. You have the original, and then they tried masking it in different ratios. So this is saying doing 8x8 squares and 50% of the image. This is 75% of the image. This is 90% of the image. So you can see when they're masking 90% of the image, it's showing the model virtually nothing. And it's still trying to recover out and figure out what used to be there. So they tried various different levels and ended up deciding on 50%. So they gave it 50%, and that was kind of the long run model that they ended up choosing. So here's kind of the whole pipeline that I just described. They have this massive pool of data, and they have to sample from it. So they want good diversity from it. They don't want to just only get desert or only forest or something like that. And so they took those geotiffs, they figured out which ones they wanted, and then they looked at it in terms of data quality. So is it missing? Is it missing values? Is it cloud covered? And then they filter those out, and then they create the czar that then they can train from, and they pull a bunch of data from this. And then they have this VIT, and they have encoder and decoder. And the idea here is they want to train this encoder very well and then transfer it to other tasks and just throw away this decoder, because all this decoder is doing is trying to map back to the original images. And so we throw away the decoder, and now we have an encoder that can be transferred to all of these different tasks. So what are those downstream tasks that we're interested in? One of them is multi-temporal cloud gap imputation. And so the high-level summary of this is, if you have multiple timestamps of something, of a given area, you want to be able to eliminate the clouds. So you got multiple images, and you want to understand what was under the cloud that was blocking something. So you have, for example, you have time step 0, 1, 2, and you give it 0 and 2, and you say what was in 1, what was covered up by the clouds. So clouds are a big struggle with a lot of the atmospheric efforts, because the clouds will block whatever you're looking at. And so being able to kind of guess what used to be there is very valuable. Another one of the tasks is flood mapping. So basically saying water came in, where did it end up pooling? Where did it end up landing? Can you look at the satellite image and understand, okay, all of the water ended up here. This area is water, this area is dry. And then another one is the wildfire scar mapping. So a fire comes through, and then they want to be able to classify it in various different ways. So is the area starting to recover? Is the area still dry? Is the area going to go back through its normal progression in the next month or 2 or 3? So there's various classifications there. And then the other piece is multi-temporal crop segmentation. So being able to understand where the crops are, and this is used in a similar way to the cloud gap. So you have clouds going over, and you want to understand where the crops are. If you take just a single time portion, then you can't accurately segment it, because one of the images might be blocked by a cloud, and you say it's not crop when actually it was just blocked by a cloud. So here's this first task, the cloud gap filling. So we have T0, this is given to the model. T2, this is also given to the model. And then T1, this is given some cloud information, but nothing else. And then the goal is for the model to actually fill in the blank and say what was in between there. And so one of the things they show here is their model is named Prithvi, and they're comparing this against a conditional GAN. And one of my gripes with this paper is that they compared models that are not equivalent at all. So this Prithvi VIT is new state-of-the-art architecture, and this CGAN is trained in a different way with a different architecture. And so they're showing that its performance is better, but it's not truly apples to apples. What I would really like to see was actually their own model compared against the randomly initialized same architecture, because this is a little bit misleading, because they could have just said, here's a bad architecture, compare against it, and now it's doing so much better. So on paper, this looks great, but that's kind of my one complaint with this is it's not exactly a fair comparison. So another task that they did was the flood mapping, and this is one where they did what I was more interested in, which is they compared it pre-trained. So this model that they loaded up the information into, um, and we can see that that is the highest performing one. And so across the bottom, we see the number of iterations. So that's how many training steps they did on this new fine-tuning data set. But one of the things you'll notice is that they compared it with the frozen encoder. So this model encoder decoder, they said we're only going to train the decoder. It turns out it doesn't work that well if you only train the decoder portion. So that concept that they had of we're going to train a very strong encoder and then just transfer it to everything doesn't entirely work. Um, and then one of the other things that they're showing is that comparing the pre-trained versus the not pre-trained, this one down here, when you take more and more training steps, eventually they just converge. So this one, the pre-trained one has an advantage very early on, but once you train it more and more, eventually the models come to the same conclusion in the end. So if you train it for 40,000 steps, you'll get them to within very, very close. And so one of the things that they were measuring was also the reduction in data. So if you take the data and I have 1,000 images, then how much does the performance degrade when I train it on 500 of those images or 200 or 100? And so they took subsamples of their fine-tuning data, and you can see the performance curves of all of these. And it's kind of shockingly close, actually, if you said we took away 87.5% of the data and you're still getting within 1-2% accuracy, that's pretty surprising. Um, so they have this performance chart here where they do a comparison that's a bit more fair compared to the previous one. So the previous one, they had the conditional GAN, and this one, they're comparing it against more similar models. So this Prithvi model is based on this VIT base. They have a VIT base version and a VIT large version. And so we can see how it compares against the randomly initialized ones. So one of the things that I think is kind of interesting is this VIT base gets a certain performance, but the SWIN, a different model architecture, gets a very significant jump above that. And then if you actually look at the difference between Prithvi, not pre-trained, and pre-trained, the delta is very, very small. Like that is less than 1%, but you got a more than 10% gain just from changing the architecture. So my read based on this is that their pre-training was actually not that helpful in comparison to just having a better architecture. Um, so here we have the scar mapping, and this is a similar graph. So showing the pre-trained versus the frozen encoder versus the not pre-trained, and we see the same pattern again, where the pre-trained one is better, especially early on, and it's slightly better than the not pre-trained, but as you train longer and longer, they kind of converge. So in reality, it's not like it gets you to a better final solution, but it does speed up your training effort. So instead of needing to train for 50 epochs, you might be able to train for 10, which is useful, but I don't think it's as useful as getting a better pure final solution. If the difference between getting the good result is training 10 epochs or 50 epochs, that's not really that big of a deal typically when we're looking at these data sets that might only have 1,000 images to start off with. It's not really that big of a deal to train for 50 epochs. So same graph as before, showing reduction in data. So with the original data set, it does get the best, but you reduce more and more and more until there is kind of a critical point where it does lose a lot of performance. So you can see that like 75% is okay, but 87.5, you're so little data that it's not really getting a good result. And again, they had another comparison with other unrelated models. I think they had so many people working on this paper that a lot of their comparisons and stuff was not consistent. So it's kind of interesting. They solved all of these different problems, but I think different groups worked on them because they're not using the same hyperparameters, they're not using the same training recipe, they're not using the same comparison models. So if you look at the number of authors on this paper, it's very large, and I think that kind of shows in some of their comparisons. So my conclusion out of all of this, we looked at a geospatial foundational model last week, and the big takeaway for me was this one was trained in a slightly different way. So the previous one we looked at, the model was trying to guess the next time step. So you're given a snapshot of the Earth, guess what it's going to look like in the next 15 minutes or 30 minutes. This one, instead, what it's doing is saying, look at this image, punch a bunch of holes in it, and then recover it back out. And my takeaway is it seems like the guessing the next frame worked better than the filling in the blanks, because the performance difference that we saw was much more significant in that one. So in this one, the performance looks good in some things, but I wasn't entirely convinced by, if you look at those performance graphs, like better architecture beat all of this thousands of hours of 64 GPUs. That's kind of my major takeaway from this.
So you said it's a 3D data? Oh, 3D or how many, like how much height is that? Because to pick up a star, for example, you're okay with the 2D, or even if it's 3D, just like a projection onto a certain plane level from Earth, even though you can see that there are variations in height, you could just project it onto a 2D and then just use it as 2D for performance reasons.
So in this, the 3D is actually it's lat, long, and then the third dimension is time.
Oh,
So it's not necessarily
It's a
elevated.
video.
Yes. Yeah. 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 Yeah.
Why do you think the models were better at forecasting than filling in the gaps on the imaging?
I think that what we saw from I can pull this one again. It's filling in local information and it's learning something, but it's not as good as actually trying to understand like what's going to happen next. I think that the actual difference in the task, this is kind of useful in local information, but not useful in like extrapolating into the future. I think that that's a much harder task.
The best we can do is imputation. Imputation is just where we take averages based on what we have and try to impute there, or if we build with more sophisticated techniques, we can try and make models of it. It works almost pretty well in practice, but it's like there are limits to it. There are still very much limits to it.
Okay. So it's better because the time series processes gives more data to the model, where it's more, let's say, predictable per se.
So one of my coworkers, they always talk about how neural networks are good at interpolation. They're not good at extrapolation. So this is an interpolation technique, basically saying like what is in between these other things. But extrapolation is very hard, saying like what's going to happen next. And I think that the act of training it on that task is a much harder thing to do than it is filling in the blanks. Neural networks are very good at saying like, okay, average between these two values, or use a little bit of context to
With a very nonlinear and complex formula, basically.
Yeah. But I think I don't necessarily think that this is guaranteed in all contexts. I think it depends on what you're trying to do. So the previous paper that we looked at, I think they just in general had a much bigger, more varied data set. In this, they were just looking at this single set of satellite images. And the previous one, they also showed that a lot of the gain was from they had multiple different data sources with different temporal resolutions, with different spatial resolutions, with different. And so the model that they ended up getting was much more generalized than this, which was only trained on this specific imagery from these satellites and then filling in the blank. And then they're actually transferring it to other tasks entirely. And in the process of doing that, they're kind of erasing a lot of their knowledge. That's what we're seeing in some of these graphs, where if you train it for 50 epochs, it gets the same result as if you just started from scratch. So I think there's maybe some way to kind of maintain the knowledge that it captured better.
Thank you.
Yeah.
You mentioned this pruning part. I'm just curious that what are the in general the trade-offs between the model pruning and the performance in that remote sensory manipulation?
The pruning, so when I was talking about that reduction, it was in the context of the fine-tuning data. So it wasn't pruning the model itself, it was pruning the amount of data that the model saw, if I'm understanding your question correctly. So you originally start with the data that has 1,000 images, and then they're measuring the performance when you scale the data down, because their hypothesis with this model was that we're going to pre-train it and it's going to perform even better with less data. So one of the problems with these kinds of tasks is it's not very common to have labeled data sets for a lot of these things. So it's very difficult to go in and say, I'm going to go label the entire Earth for some specific thing. And so they're trying to say like, well, if we could do something that could learn from just 100 examples better, that would be very valuable. So that's what they're doing synthetically here, basically saying we have 1,000 examples for these kind of limited things. How low can we go in terms of data before we start really losing performance? And does our pre-training actually help with that phenomenon? Yeah. All right. Raised hand. Yeah, Matthew.
Hi there. Hey, great presentation. Hope you guys are all doing well. I had a question regarding a comment you made about like the previous paper last month that you discussed in regards to multiple data sets being consumed in order to, I guess in this case, output like what the future time series will look like. In regards to multiple data sets that are being joined together, food for thought, like what are some of the processes they use to kind of like um I guess generalize, as you had mentioned. It's like if you can't, if you don't have all the data in certain contexts, like how can you, is it just a bunch of sampling? I'm not sure if my question is very clear.
So
Um,
the one of the magic pieces from last month was they had this perceiver module, and the idea behind that was we have lots of different variables and we have lots of different resolutions and we have all of this variety of data. We want to use all of it, but we don't know how, because we can't line things up where it's like this one's
Right.
measuring the IR of this, and this is actually radar, and this is something else. And so they had this perceiver module that was basically like a before step, where it was like, we're going to take all of this and we're going to just convert it to some common representation. And that was their like perceiver encoder was basically the magic part there, where it was like, we're going to learn something. We're going to learn this module that tries to convert everything to a common format. So that's what I would say was kind of the trick to integrating all of those different data sets, was that perceiver module that can handle all kinds of different inputs and then try to convert it to a common format.
And that
Sweet, thank you.
format was an embedding, was it like not necessarily human interpretable?
Yeah. So that perceiver module made some embedding that then went to some other model, and that
Yeah.
second stage model was kind of the common piece, but
Yeah.
it took some embedding that didn't mean anything necessarily.
Got it. Thank you.
Yeah.
All right, great. Last chance for questions. All right, thanks, Ryan. Okay, I'll share my screen in a second. All right, awesome. So, and today I'm going to talk about this one particular architectural innovation from this Deepseek V2 paper. So we're not going to cover the entire Deepseek V2 model or the entire paper, but I've been on a little bit of a kick lately looking at LLM inference and optimizations and stuff, and they do something that's pretty interesting. And so I think this bears paying more attention. We'll see whether or not other people really pick up on this if it turns out to have legs or not. So they created something that they call multi-head latent attention. And so Deepseek V2, they're a company in China, and they had Deepseek version 1, right? And so this is the Deepseek V2 paper. It's from June, and because everything these days is moving so crazy fast, I think this past week Deepseek 2.5 actually just got released. So like before I could even do a paper on it, they already have a replacement for it, which is it's not necessarily that big of a change from V2, but anyway, that again, that just shows. So we're not going to talk about the whole model, but just to give you a sense for it, it's big. It's 236 billion parameters. If you're familiar with Mixtral, it is using mixture of experts, so it's not just a fixed 200 billion parameters. They trained it on a very large corpus, over 8 trillion tokens. And so they have this mixture of experts that they use. If you're familiar with Mixtral, it did whatever, like 2 of 8 or something like this. And they had a more aggressive, so their 200 billion parameter model, they had some small number of fixed shared experts. So these MLPs, like a regular LLM, are always on. And then for the switched ones, instead of having just like 8 or something like that, they had a number like 100 or something like that. So it was like 2 plus 6 of 100 or something like that. So a very aggressive. I'm sure they must have done a lot of experiments to figure out how to fine tune, the experts part. It's long context, right? So that's definitely what everybody's asking for. Can you have long context? So 128K. I don't know these days if that's not as newsworthy, as it's not considered quite as long or whatever. And then not only using KV caching, which I've kind of talked about the last 2 months, I think, but then they implemented this thing that they created called multi-head latent attention, and that's what we're going to talk about today. Is just this attention mechanism that they do differently from most transformers. And so this MLA, multi-head latent attention, that's the reason why their KV cache on their 200 billion parameter model, they say is 15 times smaller than just a regular vanilla model. And that allows them to actually generate tokens 5.7, so a little short of 6 times faster than a normal LM. I mean, 6 times is a pretty big speed up. All right. So what is this multi-head latent attention? So we'll go into the details, but high level, All right. So when you do inference on long contexts, having a KV cache where you save your keys and values is faster than recomputing the keys and values every time you're generating a new token. So if you say, what is the definition of I don't know, whatever, an eigenvector, and then your model spits out an eigenvector is right. Every single one of those, you need to attention needs to look at all the context, all the tokens that came before. So you're not going to recompute those. You're going to cache them. But even though this is faster, this still becomes the bottleneck. Okay. So then it's just a question of how fast can you literally copy, can you load these keys and values onto your GPU? And so the smaller your keys and values are, the faster you can actually load them. And that's where they get their speed up, is this trick we're going to talk about reduces the size of the keys and values that they save. There has to be some catch, right? You can't just magically shrink things by a factor of 15 or 10 or 7 or whatever, right? So what ends up happening is this latent, they have to then sort of expand it out back into the full-sized keys and values. And so there is a little bit of operations that are needed to do that. But if you're familiar with things like flash attention, and I think it's now on like flash attention version 3 or whatever, what we've seen lately is that if you want to make your model run really fast, for the most part, what you're optimizing is minimizing GPU memory loads. You're not actually minimizing flops. So all the variants of flash attention actually do more matrix multiplies. They increase the number of flops. But what they do is they decrease the number of memory loads on the GPU. And because a memory load is like 100 times slower than a matrix multiply, you can easily afford to increase your matrix multiplies by 10%. And then your model's going to run a lot faster if you can decrease your memory pressure. So I haven't said how they do this reduction, but that's just sort of a high-level overview of what we're going to talk about here. All right, so what are some of the prior approaches? What have people done before for reducing the KV cache? So a very simple thing you can do is multi-query attention. So you basically say, I have 16 attention heads in every layer. I have 16-way multi-headed attention. I'm going to have 16 queries, but I'm only going to have one key and one value that all 16 of them are going to share. That's going to reduce the amount of memory I need to load from the KV cache by a factor of 16. That's going to be awesome. It's going to be so much faster. The problem is, we're going to see on the next slide that it also doesn't work as well. And so your LLM performance drops. So then people said, okay, well, why don't we do something in between? Instead of dropping it all the way down to 1, I could cut it in half, or I cut it in quarters. So I do 16-way attention, and maybe I have 8 keys and values, and each key and value is being shared by 2 queries. So you have the diagram down below where you can see, like, this is not 16, but if you had 16-way attention, you'd have 16 queries. They're all using 1 key, and then once you calculate attention, they're going to have 1 value. Or you could do something like this where you say, okay, I'm not going to be quite so aggressive and reduce it down to 1. So in this paper, they actually demonstrate some benchmarks that they did. Not going to go into too much detail, but these are not even terribly difficult benchmarks. MMLU, language understanding. You can see here that the regular full attention, which they abbreviate multi-headed attention, MHA, the regular full attention gets significantly better scores than when they do grouped query, or the more extreme thing where they only have a single. So they were motivated to say, we want to reduce the number of keys and values, but we don't want to take this performance hit. So what can we do instead? So the idea here is, since you can't reduce the number total of keys and values, let's keep the number of keys and values, but just find a way to compress them. How can we compress them? Well, they ended up with a very simple techniques. They're just doing a matrix multiply. So let's say that your keys and values are originally length 512. So you multiply it by a 512 by 128 matrix, and then your output's going to be only length 128. This can be 4 times shorter. Well, what if we did multiply it by a learned 512 by 64? Now it's going to be 8 times shorter. What if? And so they tried different lengths, and they were able to reduce it by like around a factor of 16, 20, something like that, and still preserve a lot of the information. So the idea is that if you think about these vectors, they have a lot of floating point numbers. There's 512 floating point numbers. But hypothetically, if the whole vector was 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, just repeating, you really only need 2 numbers to represent that because it's just rank 2. So you could actually multiply that by a 512 by 2 matrix, and then to reconstruct it, you multiply it by a 2 by 512 matrix, and you would be able to exactly reconstruct. So the question is, what is the intrinsic dimensionality of this information? And I think this is interesting because a lot of people already I think know is the right word, although I haven't read the literature. They know that the keys in particular are a very low intrinsic dimension. I'm not 100% sure about the values. I haven't read as much stuff about the values, but if you guys are familiar with the curse of dimensionality, okay, when you have things that are high dimensional, and by high, I'll say like anything over 10, but we're usually way beyond that. We're like in the hundreds. Then you get these things that just do not make intuitive Euclidean sense. So like almost all vectors are super close to orthogonal. The dot product between any 2 vectors is very close to 0. Another thing that happens in high dimensional space is that the length, the distance between any 2 vectors ends up being very similar for any 2 vectors, okay? But the whole point of attention is that you dot your queries and your keys, and you're supposed to get different values so that some of them have high values, and those are the ones we say we're going to attend to. And then you're going to have some low values that you say we're going to ignore those tokens. And then the whole softmax thing is just a scaling thing so that everything adds up to 1, okay? But if you had full rank vectors that were length 512, what would tend to happen is almost all of your attention scores would be similar. You wouldn't actually get really good differentiation where you're like, oh, all the attention is on boy, and there's very little attention on the word walk. Okay, so that's how it's intuitive for me, and I just haven't found where in the literature I think people have said this. But so we kind of already knew that the keys and queries had to be relatively low dimensional. They have to kind of be less than 10 dimensional, because if they're not, you're not going to get such pointy peaked attention scores. Okay, so that's what they do. And in this technique, they found that they were actually able to compress these down without paying the kind of penalty that the multi-query and the grouped query techniques work. There is a slight caveat here, though, because mostly when I talk about attention, I just focus on the queries and the keys. But the reality is we have to have positional embeddings. For the original Vaswani attention, you had embeddings that were added at the very bottom. So you embed each word into a dense vector, and then you add the embedding. These days, because of things like length extrapolation and other reasons, rope is very popular. Rope's a little easier to work with because what you do is you just, you don't directly modify any of your token embeddings at any of the layers. But right before you do attention, you apply a rotation matrix. You do a matrix multiply, but it's a rotation matrix. And basically, the number of degrees that you're rotating something depends on what the token position is. So for position 1, you rotate it a little bit. For 2, twice as much. For 3, 3 times as much. For 4, 4 times as much. And then you do the same thing with the keys. And so what ends up happening is when you rotate both of them, then the only thing that matters in terms of how different they wind up being in the end is how far apart the query and the key are. So if they're 1 apart, they're both going to get rotated, but they're going to get rotated almost the exact same amount to each other. Whereas if one of them is very far, one of them is token 1, the other is token 100, then the amount of rotation is going to be very different between the two. And so then the idea is that the transformer can learn to measure these rotation differences if it wants to know how far apart the query and the key are. So that's how it can measure that this word came 5 before, my current word or something like that. So these rotations get applied right before you do the query and the key dot product multiplication. If you actually stored those in the cache, they had the problem that this would cause your keys and values to, your keys in particular, it would cause them to look very different because sort of the same information at token 10 is going to be different than the same information at token 100 because they have different rotations applied to them. And what they want is they want to like learn this pattern. They want it to be as low rank as possible, but you start adding these rotations and it's adding to sort of the complexity. It's adding to the rank of the information in the keys. So ultimately they had to come up with a trick where they sort of separately did rotation information, rope information, and they did base keys. And whereas in vanilla rope, you rotate the actual key. Instead, what they did is they said, we'll just leave the key alone and we'll have some extra rotation information and we'll concatenate it. So then basically, if the model wants to learn how far something is, how far a token is, it'll just use this last part that has all the position information. And if it wants to know the content of the word, is it a noun? Is it a verb? Is it very masculine? Is it very blue? Is it very small? Whatever. Then it'll use the left-hand side. It'll use the content portion. So actually, when I first learned transformers, I just assumed that the positional bending was concatenated to the semantic information. I was very surprised when they're like, nah, we just sum the two vectors. I was like, what? Like, are there zeros in lots of places? And they're like, yeah, logically, but don't worry about it. It just works. And so this is actually kind of going back to my more simple intuitive thing of saying that instead of just summing them, rotating them, whatever, saying that if you think about it dimensionally, the model can separate out the two things. Now, as a human, we can easily see the separation because we're literally saying the first, whatever, 256 is the meaning part, and the next, 48 is the rotation part. So that's this extra trick. I didn't go into all the details of exactly how they do that. But so when you combine these, you get a diagram that looks something like this. So here is your input to the attention layer, okay? And they're going to multiply this by a matrix that's going to make this shorter. So this C that we're talking about on the left and right for the query and the key is going to be smaller than our original token. That's the whole point of this. They want this to be small, and in particular, the keys and values are going to go in your KV cache. I think maybe that's why it has these slashes on them, because this is what actually goes in the KV cache. Oh yeah, up here, the legend, cached, if it has slashes. So this thing is smaller, a lot smaller, it turns out, like more than 10 times smaller. And that's what we need to store in the cache. And then ultimately, logically, we need to reconstruct the full length keys and values. Okay, so there's another matrix multiply here. Then we can just do regular attention on keys and values where we dot product them, we do the softmax. That's conceptually not changing at all. But you'll notice that there's this little thing here that says, here's my regular key and here's my rotation information for the key. And here's my regular query and here's my rotation information for the query. So again, vanilla rope would have modified this query and modified this key. But they did not want to do that because that affects their ability to cache stuff. And so instead they concatenated these special rotation information. So here's the storage reduction. Basically, if you go through these formulas, if you L is the number of layers and D is the dimensionality of each head, like I was saying, like 5, 12, whatever. So if you look, these two variables appear in every single formula. Okay, so you can basically just sort of ignore the number of layers and ignore the size of each head. And they're saying for the multi-query, we're going to store two things, one single key and one single value. Okay, for regular full attention, it's going to depend on the number of heads. So if we have 16 heads, we're going to store 16 keys, 16 values, so it's 2 times the number of heads. And if we do the grouped thing, then it depends on how much you're grouping. So if you have 8 groups, then that's going to be half as much as if you did fully everything. Okay, so the idea here is that let's just use 16-way multi-head attention. Okay, So the top row regular is going to be a 32 times the stuff on the right. The next row might be 16 times the stuff on the right. The bottom row is 2 times the stuff on the right. And this guy here is only 2.25 times the stuff on the right. So it's almost as small as the one. Oh, sorry. It's 4.5. It's 2 times bigger than the smallest one here, the multi-query. Thanks for catching that, Sankarshan. Yeah, so it's a little more than double this really, really small one, the multi-query, where we only kept one key. Okay. So we're keeping a little more than the equivalent of 2 keys. And then the question is, right, well, how does it perform, right? So this is the part that I thought was a little odd. They have this table, it's in the appendix, and what they said is grouped query, you take a performance hit. Multi, you take a massive performance hit. They didn't just say we didn't take a performance hit. They actually said, this exceeded the performance of full attention. We did better. Now that's possible. It's possible that if they're sort of like promoting the right inductive biases or whatever, that by lowering the rank, it's actually helping the model learn faster and learn better relationships or whatever. But if this is true, I think this is like much more surprising than just the fact that, hey, we actually saved, like whatever, 12 times, 15 times the amount of memory for our KV cache. I mean, that is impressive that the KV cache loads 6 times faster or whatever. But like, really? So then I would do this even if I didn't get the memory benefit, if it's actually going to give me a better model. So one of the things I say is you should always be a little bit skeptical about results in papers. Ryan, you mentioned like, hey, this one here was not a really great comparison because they actually compared it to a 5-year-old really crappy model. Like, of course you beat it. Like, that's not really a fair comparison. Who knows if they cherry picked these results, if maybe they had 12 benchmarks and their thing did worse on 8 of them and they just only published the 4 that they did, right? So you always have to take it with a grain of salt, but nevertheless, this will potentially be a useful technique on 2 levels. Even if these results are cherry picked and actually it only has 98% performance of regular full attention, that's probably good enough that for a lot of use cases, to get 6 times faster inference. I mean, right? Like if you think about how many like billions of dollars OpenAI is losing every day because they're giving all the money to Microsoft for compute every time you use ChatGPT, right? If they could cut their compute costs by a factor of 6, that's billions of dollars that this would save them. Okay. So it's useful. It's useful just for that, right? It's also useful if somehow this actually works better than attention, whether you do or not. But so for all but the most intense things. So if you're doing coding, protein folding, you're going to need the absolute max performance, whatever, everything. You wouldn't take the slightest hit. But for many people, they're asking ChatGPT, like whatever, are there dogs that don't bother people's allergies? And you don't need that fancy of an LLM in order to be able to serve general purpose needs. So this really stood out for both of those reasons as something to pay attention to. Again, I'm not 100% sure that this model is as great as the authors say it is. Especially, I mean, there's many reasons to be skeptical in general, and this is a private company. This isn't even like a university research paper. But I do think this technique is interesting, and like I said, it at least lined up with my intuition that queries and keys should be low dimensionality. Even though they're relatively big, we expect them to be rank 5 or lower or something like that in general. Yeah, so kind of round things up, I have some slides in the appendix. But basically, they reduced the size of the cache dramatically. Interestingly, they said they actually didn't just match, but outperformed it. And so their shorter vectors are about 7% the length of full length keys and values. And there is some stuff I mentioned they had to do with rope. There also is some things they can do where you have to do this matrix multiply to reconstruct the original. vector from the short one, but it turns out that that matrix multiply that you do is either immediately preceded or immediately followed by another matrix multiply. And when you do more than one matrix multiply in a row, their matrix multiply is associative. And so you can actually multiply the two matrices, weight matrices together instead of multiplying them by your data sequentially. And so just like there's this trick in LoRa where you have this adapter thing and you technically are supposed to sum it with your regular weights, LoRa says, but you don't have to do that at runtime. You can just pre-compute the sum of the two and you can store that. What they're saying is they actually figured out ways they could pre-compute the product of the two matrix multiplies, and they could store that instead of having two separate weights and actually having to at runtime multiply them over again. Bottom line is, you can look at the paper if you want to see more of the details, but the bottom line is that you would think that there's a lot of extra compute to reconstruct the full length keys and values, and there actually isn't, because they managed to fuse those operations into something else. There's still a little bit of extra stuff because remember there's those little rope position things we concatenated. So they still need to calculate those, but they didn't actually have as much extra overhead as you might vanilla implementation think. Yeah, so at the end of the day, this Deepseek V2 model, because of the heavy mixture of experts, it's only using 21 billion parameters during inference. Okay, they have the 200 billion parameters, but you're only, when you do a forward pass, you're only using 21 billion of them. And I didn't print it here, but they have performance that in many ways seems to sort of beat Quen 1.572b, be comparable with Mixtral, which again, it's using 22 billion, but it's got 8 experts. And then it seemed to me that they were slightly beat out by Llama 3, 70 billion, but Llama 3 does have whatever, 3.5 times as many weights. So to be slightly beat out by a model that's 3.5 times your size, I don't think that's embarrassing. So I'm not sure that, again, not necessarily saying you should run out there and go to Hugging Face and download the Deepseek V2 model and use that as your only model for every task from now on. But this is an interesting technique, I think, to keep an eye on. And so next month, I think I'll try to do something that's not LLM inference, mix things up a little bit. But this one just seemed kind of really interesting, and so I decided I would stay on the topic one more time. All right, any questions?
Will this recognize the sparse data, for example, in input vectors, features? That's how you're reducing the parameters, or what is that? How would you do that?
Yeah, so there actually is a matrix that you multiply your keys and values by in order to get the smaller representation, and that's learned. So when you are training this LLM from scratch, you're training that. And so presumably there is whether we call it sparsity or low rankness of the keys and values, and it takes advantage of that. And if a regular LLM perhaps wouldn't organize the keys and values to really, really cleanly be low rank, this model will have an incentive because they're getting squashed, right? So it's possible that we might say, oh, today if you use Llama, the keys live on a 5-dimensional manifold, but it's not linear. It's actually curved, right? This model will have an incentive to have that manifold be linear because it can only use a matrix multiply to compress it. It can only use a linear operation to compress it. So then, even though they're not necessarily saying that your model today already has a linear key representation, but this one will be incentivized to learn a way to make it be linear because that's what they're doing. And so my interpretation of the paper, they're not saying that your model already has linearly compressible keys, but they're simply saying that they're low enough rank that if we force this model to do the low rank reduction, that it can figure out how without it suffering a performance penalty. Right, without a loss of information. And in fact, somehow even a gain.
That's very good.
Yeah. Yeah.
So my question is, how do you find it?
So the question was about the analogy with flash attention. So actually, flash attention, it's not the CPU GPU memory copies. It's actually from GPU RAM onto the fast SRAM, the cores where the matrix multiplies actually happen. And so I have not implemented a KV cache. I don't really know. There's actually two levels of KV cache. There's you keep the keys and values on the GPU, and you just need to get them loaded up so that you can do your attention calculation. And then my understanding is people actually do use the second level where they keep the keys and values in main memory, and copying from main memory to the GPU, I think it can be pipelined and whatever, is still faster than recomputing every key and value from scratch. Because again, for long context, if you have a very short question, what's the capital of France? No, just calculate everything because you can do it in one batch. But if you're doing RAG and you have something that's length 128,000 or even longer, you don't want to be sitting there calculating 128,000 keys and values. That's very expensive. And that also involves a lot of memory movement as well, because the cores are not that big or whatever. So my understanding is that this is predominantly about what they call high bandwidth memory, HBM, movement to SRAM within the GPU, that we're cutting down the amount of that. Does that answer your question? Yeah, so this is giving you that, whatever it said, 6 times faster inference. It also is faster to train. I didn't really go over those details, but they also worked on how to optimize the training, and they did some other tricks that I think to try and speed up the training as well. But this multi-head latent attention, this MLA, actually was good in terms of fast training as well. Yeah, I don't. Yeah, there's no key value benefit when you do training, because generally speaking, when you train, you do teacher fortune and you do full size batches. So if your max length is 128,000, you put in 128,000 tokens all at once, and then you don't ever do further inference on it. You just flush all of those, and then you put in a fresh new 120. So the key value cache benefit is purely for inference. But they did, in the paper, they talk about how they like, this model's bigger than Deepseek V1, but it actually trained in like half the time because of a lot of the tricks that they did. All right. I saw there were some things in the chat, but I wasn't sure if they were questions or. Let me see if I can get to the chat. Okay, sorry that I missed these in real time. Question, this is for single machine KV cache implementation. Does distributed inference implementation also do similar cache hits? I'm not exactly sure what the most common distributed implementations are. If a common way you do it is you basically say, my model's so huge, I can't fit it on one GPU. I'm going to put layer 1 on one GPU. I'm going to put layer 2 on a GPU. I'm going to put layer 3 on another GPU, right? I think that's a pretty common way that people split it up. Then you have a KV cache for every attention. And so there's a KV cache for layer 1 and a KV cache for attention for layer 2, whatever. And so once again, that GPU for very long context, for short context, it's not an issue. But for long context, where you're talking about 100,000, million, 2 million, it will be memory bound by loading the KV cache. So I would imagine that if you did those types of distribution of your model across multiple GPUs, that you would see very similar benefits because inference is just very memory bound. Some of the other stuff I've been reading about is like, well, if you have the right workload, you can do prefill where you're doing a lot of attention computations, and you can pair those with inference where it's very memory, and then you can kind of get the best of both worlds by trying to balance them and whatnot. But ultimately, I do think that, especially when the output of your LLM is long, that means you have to do a lot of inference. If the output is short, if it's just 10 tokens, that's great. But if you're outputting a big long paragraph, if you're outputting like 2 pages of code, then you're going to be hitting the KV cache a lot, and you're really going to benefit from anything that reduces that bandwidth. Thanks for the question. You can either raise your hand or you can post in the chat if I didn't fully answer that, or if there's a follow-up. All right. Any other questions? Yeah.
On the rope piece.
Yeah.
I was just skimming through the paper. They kind of said this is a problem and then solved it, but they never did any experiments to show that it was actually necessary. They didn't have an experiment that this failed because. So I'm curious, do you think that it would have been possible with vanilla rope? It just wouldn't have learned a good representation, or
right,
complete failure?
That's a great point. I struggled with that section a little bit myself because they didn't actually demonstrate that it's a problem if you rotate the keys. But it seems reasonable because rope basically does pairs of dimensions, and it rotates like your whole thing. So if it's 512, it does 256 pairs that are just like whatever sine cosine pairs. And so I imagine that on the surface looks full rank because it's not a linear. I'm not sure, but like I think that it is possible that since rope doesn't just rotate some of the dimensions, but it rotates all of them, it seems reasonable that that's gonna cause a problem. But yes, I agree. I would have rather if they actually said, look, here's the amount we could compress the keys if we use vanilla keys, and it's like we can compress it 15 times. Here's how much we can compress it if we rotate them with rope. We can only compress it 2.5 times. And so then what's the solution? Split out the rope, right? I would have actually liked that better in the paper.
And then the piece about getting better performance out of it would have been interesting if they did something where they, because from my perspective, there's kind of 2 things that could be going on there. Is that it's useful to bottleneck that. So bottlenecking the dimension there is useful, or it's just an extra 2 linear layers that you threw into your model. So that's kind of the like, is it useful because it bottlenecked, or is it useful because you threw 2 extra dense layers in the middle of your attention calculation?
That's an interesting question. So in compressing it, you are adding nominally 2 weight matrices. So in the appendix I have here, you can see the full calculation. And so here's the shortened keys and values. And so you've got this DKV matrix that you're using to shorten it. And then nominally you're reconstructing it with this UK. So this is what you're talking about. You get these 2 additional weight matrices. Yeah, you're right. They actually did not tie these two matrices. They could have had it where like there's some kind of like inverses of each other or whatever, and they didn't. So I wonder if they included these DKV and UK um, weights in their parameter count. But then they also did this thing where they fused these into another weight matrix, so then you're not really getting like another whole of free. But that's an interesting question to look at the implementation to see whether or not the parameter count really matches or if there's some hidden extra parameters in here. But that, yeah, that's a great point. That might explain how they got a slight bump in performance. But it's plausible that by forcing it to do a linear reduced representation, the bottleneck, that this is like an autoencoder that actually somehow got the model to do something smarter. Yeah, I don't have a intuition about that yet.
Yeah. Fair.
Yep. Cool. All right. Any other questions? All right. We'll wrap things up here. Thanks everyone for attending. And again, we will have the monthly talk the first Saturday in December. In 2 weeks, we have the first session for the mathematics and machine learning book. And then I don't have the December date set yet, but that will also be monthly, sort of at this point alternating with the monthly paper talks. So thanks everyone.